Yep.
Testing to bypass the system. Hello. Okay. 1 second. Cool. Yeah. Hello, everyone. Thank you for joining the call on Sunday. It's supposed to be on Saturday, but it's not working out for me on Saturdays. So, and also, this is my first technical presentation after a long time. So, I'm not good at presenting. I'm very nervous. So, yeah. But I'm trying to overcome that. But anyway, so today I'm talking about my favorite topic, embeddings. I will not be going too technical into this, but I'll be covering the critical parts within embedding Gemma. A couple of weeks back when I was speaking with Arath mentioned that it would be good to kind of introduce a little bit about how embeddings are trained and other things. So, initially I'll just go over how embeddings are created. Then I'll talk about embedding Gemma at a high level with respect to the key innovations that these guys did and some of the advantages and other things. So yes, yeah. Okay, so there are a lot of reasons why we use embeddings, but you know yeah. So basically, there are different types of embeddings like sparse, dense, and yeah, just like simple one hot encoding and stuff. So basically, 1 minute. Yeah. So, for something like one hot encoding and stuff, we don't retain like any semantic information and other critical things that are relevant in like, for something like retrieval tasks. Then, you know, yeah. So dense embeddings basically, yeah, they are like, sparse and other things. And apart from that, you know, um these dense embeddings like learn from data as well, which like typical encodings don't learn. So that's why we use more larger embeddings. So yeah. So there are, yeah, like I mentioned, there are different types of embeddings. One is like simple, like one hot encodings, and there is like BM25 based encodings and stuff. But like embeddings, like I mean, yeah. So there is one, the other type that is LLM based, embeddings. Yeah. So the way that these LLM based embeddings are created is by deciding the architecture. Like, there are decoder only, encoder only, and encoder decoder. And the way they're created, the final ones are encoder only. But the way they're, started, like, start can be any one of them. And yeah, but by the way, please ask me questions and also correct me if I'm wrong. This is this is something that I'm doing.
Yeah,
And yeah,
don't worry.
so
I will ask you questions.
okay. Hope questions that I don't know. Okay. But anyway, so yes. So then we have, input tokenization. So whatever the text, we convert it to tokens, like similar to LLMs. And then we have like, contextual representation, which passes through transformer layers and, goes through hidden states. And finally, like, we get embeddings, and we select a specific hidden state, and that we use it as embeddings. And there are like post processing methods like normalization and dimensionality reduction. But yeah, basically at a high level, we take an LLM that's already trained for token generation, and we convert it to encoder only model. And then like we uh, take out the layers that are important, and then we do post processing, and that's how we create embeddings. So yes. Okay. So there are like, various use cases for these embeddings. Some of them, like, you'd have heard about RAG and stuff, but more critical things like, hard negative mining, where so hard negative mining is basically creating data sets where, embedding models typically say two queries are same, but, similar, but they are completely opposite. So there are easy negatives and hard negatives. So finding hard negatives are the most difficult part, but they are the most helpful for like, for these embedding models. So, we use embeddings to also create these data sets for, smaller embedding models. Yeah. So, but apart from that, other things are pretty straightforward, like, information extraction, paraphrase detection, and other things. Basically, these all depend on semantic meaning from that we extract from embeddings. Yeah. So the data set that, you know, yeah. So the data set that we use is, sorry, not data set, but basically the MTEB benchmark. So basically, this covers, 8 core task types, but also has a lot of internal tasks, and, covers 20 domains and a lot of languages. I believe the most, all the languages. But the core task, like, go over like, retrieval, clustering, pair classification, re-ranking, semantic textual, and, yeah, yeah, by text mining as well. So the other like so the evaluation metrics for this is mean over the all the task types, and mean over type, uh, like internal types, and the last one is border count. So border count here is like, ranking based metric. So yeah, it compares different embedding rankings. Uh, yeah, and gets this score. Yeah. Any questions? So yeah.
Can you explain like so how do you calculate what were you saying board account? What's that? Can you explain that again?
So basically, this is this is just a metric based on retrieval score. Like, I mean, like retrieval ranking, and
Hmm.
it is based on across like, different embedding models. So it's a simple thing, but it has a different name. So yeah,
Okay.
it's based on ranking. So yeah.
So, can you explain what's ranking? I don't know
Um,
what ranking is.
so imagine there are two embedding models, 2 to 3 embedding models.
Uh-huh.
Then the first embedding model like gives like, 1, 3, 2, 4, and the other embedding gives like 1, 2, 3, 4, right? So the border count of the other embedding model outputs are much like, that's higher than the first one, where it's basically matching with the original ranking. So
Oh, so
that's
you
what it
have a
is.
ground truth for a ranking also, which from which you're comparing
Yes.
to. Okay. Okay.
Yes, yes,
Makes
yeah.
sense.
So it's basically, ranking comparison. Yeah.
Okay.
So there are like, I believe there are like more, detailed metrics internally, but these are like at a high level, metrics.
Hmm.
So the paper that I'm covering is a recent one. I believe it's September paper. So it's based on Gemma model, Gemma LLM model that Google DeepMind converted it to embedding Gemma. And the main, okay, so the main goal of this paper is to kind of, create lightweight text representations, and but also, as powerful as like similar, like, like as powerful as like closed source models, like, Gemini based embedding models. So but obviously they're inferior to them, but with respect to the size and applications, it's superior. But yeah, so this is based on 308 million parameters encoder only transformer. But yeah, I'll get into why, the overview, like, I mean, architecture, other things later. But at a high level, it's 24 layers and 768 dimensions. These are like output embedding dimensions, and yeah, intermediate like 3000. Yeah, but this is sort of currently under 500 million parameters. There are derived models that are currently sort of, but yeah, when it came out, it is sort of under 500 million parameters, and it's good at multilingual English and code. As I said, it's very similar. Like, it's almost same as like, 600 million parameter models. Yeah. It also supports like, MRL, that is wait, Matryoshka representation learning. They call this as, Russian doll based like, learning thing. So basically, 768 dimensions can be used for different, tasks, like, 128 dimensions for on device embeddings and stuff. But I'll get into this deeper later. It's the same topic. Yeah. But so some of the core innovations that these guys did is encoder decoder initialization via T5 Gemma and geometric embedding distillation and spread out regularization. So I'll get into these things later. Yeah. So at a architecture overview, this is Gemma. This is based on Gemma 3 decoder only model. So they use the decoder only model with the, with the help of UL2 pre-training to create encoder decoder based model. Then they remove the decoder part. They just use the encoder for the embedding model creation. Yeah. But this approach was used to give the insight of like understanding the text from left to right and right to left. So yes. So yeah. So based on one of the ablation that they had, encoder to like encoder decoder model had like 0.7 point improvement compared to just decoder only model. Yeah. Yes. Okay. So the training recipe of this particular thing is so there are three different losses: contrastive loss, spread out regularization. This is their innovation. Then embedding matching distillation. This is as well like one of their innovation. Yeah. So to tell about embedding matching distillation. So basically the way it is done is to kind of think of it as like distillation with a larger embedding model, right? Trying to copy the structure of internal um, learned representations of Gemini model to Gemma model. So this is more about like getting that structure from Gemini model to Gemma model. So that's what is embedding matching distillation. So Gemini behaves like a teacher model, Gemini embeddings, and yeah, geometric structure. Yes, it copies like not copies, like transfers it. Yeah, and yes. Okay, so basically, data pipeline is entire Gemma 3 corpus. I don't believe they have gone in depth into the data part, as it's it's critical to their I believe it's the secret part. But yeah, pre-training 300 billion tokens and fine tuning is 20 billion tokens, and model swooping. So do you know what is model swooping? Anybody here?
Nope. Nope.
No.
Okay, yeah, it's basically like so what they did is like they train 11 different models instead of just one model with a lot of hyperparameters. So by doing 11 models, uh, whatever the weights that they got, they just averaged it and they created one final model. This gave a like zero point 0.8 improvement compared to just one single model with completely like complete like hyperparameter search. So yes. So this is like the high level overview of training part. And yeah. So this is one of the innovation that these guys had, that is spread out regularization. So the reason to have this is there is a problem called anisotropy. So basically the problem is this cone structure where like um, there is a narrower end where like all the representations are like condensed into a small space, and what happens is it's harder to kind of quantize it because they're all densely packed into one small space in high dimensional space. So yeah, hope you get what I'm trying to say, but if you don't, just ask me. So it's more of like this clumping problem. Imagine if this is the entire room, and whatever the representations it's learning, it's trying to only keep it in a small region. So any kind of diverse queries that you have, they all be in the same space. So that is one of the big problem, because it's hard to distill or like yeah, distill into int quant model. So basically that's what they did. So the solution for this is spread out regularization. This makes the whatever the learning happens like spread out, and there is this thing called second moment. It optimizes the second moment. I believe it is a statistical thing where it tries to increase the space, or spread out all the representations or the points in that high dimensional space. Then yeah, so basically by using this particular method, they had increased like by retaining the same accuracy, they able to decrease the model size by going into 4-bit quantization by like 4x, yeah, model size. Yeah, some of this benefits of using this method is robust quantization. So yeah, when you have like large space where there are representations, it's easy to compress them because there is a lot of empty space. But if the model just focused on a small area, it's harder to quantize it. So that's the whole idea of this. And yeah.
Just had a question. Like, why do we have like any reasoning as to why these embeddings naturally clump together? Like, is this like a limitation of previous models? Like, is there like some justification for why this tends to happen?
Hmm. Yeah, I didn't focus on the justification, but basically, I believe that previous models had this problem where naturally they start clumping together like nearby. So yeah, this is like part of the earlier architectures. Yeah,
Okay, I see. Thanks.
So there,
yeah.
this is like representation collapse. So most of
Okay.
the representations are pointing toward the same direction, or they collapse in some way, or something happens. So what their idea is actually doing is very similar to what Jan LeCun did in the recent paper Lejepa. So
I see.
they are the so what they are doing is just making it a unit sphere with some regularization, and in Lejepa what they are doing is having a constraint of the that the representation needs to be isotropic Gaussian distribution. Is the same thing. It's just this exactly same thing, having a sphere representation.
Mm, I see.
Okay.
Okay, that makes
So yeah, exactly what you mentioned. It's yeah, it's basically spreading out the representations.
Yeah.
Uh, that is a problem that the previous models didn't resolve. Yeah, like I didn't read the Jepa paper, so
Mhm.
I don't know. Yeah, but yes. Wait, 1 minute. So the other support that they did, with this is Matryoshka representation learning. It's hard to pronounce, but yeah. So basically, the way that this representation learning, they do is by applying uh, multiple losses for different dimensions. Imagine if you take 768 and within that 512, so there are different levels within this 568. So what what this kind of learning does is, you can take the first 5 or even 10, still they have meaningful information. The previous embeddings that you get, you need all the embeddings to kind of be there to kind of get useful results. I mean, not useful, but for the embedding model to work. But with this approach, you can take any number of dimensions, and it still works good. The preferred ones is like 128, 256, and 512, and 768. That's how it was trained on. And the way it is done is applying contrastive laws for three different things. That no sorry There are three different losses. One is contrastive loss, one is similarity loss, and there is one based on geometric distillation loss. So this is applied like summation of all these things for all these four levels, and then like calculated and trained. Yeah, so each level is independent, and yeah, early dimension captures the most. So yes.
So is it like you have these 4 5 linear layers at the end which are separate, and you're training all of them together with the same base?
Can you come again? Like, it's just one hidden state, I believe. It's 768 dimensions, but the way they do it, I believe, is like prioritizing the first, or from the beginning. not as like completely whole dimensions.
Okay, so
You
it's
get what I'm saying?
so 768 is one big vector and you are taking
Yeah.
128 from that, or
Yes. So it's like
okay.
the first 128, then first one 256, then first 512, yeah. And
Okay.
768 is the complete one. So
Hmm.
they are prioritizing that. That helps in like there are a lot of benefits to this. So yes.
Hmm.
Okay,
So
just a
along, yeah,
question. Yeah.
yeah,
So
yeah,
it's
go
just
ahead.
a like you said like hidden layers were different or the same layer, like the final layer they are doing it. Because
They're doing it
128.
for the final
Mhm.
layer.
Okay. Okay. And then adding like four at 4 levels.
Yes, correct. So they're taking loss of three different losses for this four different levels,
Mm-hmm.
and they're doing it. Yeah. This is
Okay.
done by like OpenAI as well for their text embedding model, but not,
Okay.
yeah. This is
Okay.
not prevalent in like open weight models. Yeah, this
Mm-hmm.
is something
Yeah.
that started
Okay.
from last year to this year. Yeah. So yes.
Okay. Good.
Okay, so by using this, they got like huge speed ups. So basically, the model size is 300 million parameters, and when you kind of use it in like handheld devices and stuff, you can generate 568. But imagine when you try to kind of do similarity search on 768 dimensions for any all your documents, it is like it impacts the performance. So by using just 128, you might have a small drop in performance, but the latency is like reduced heavily. It's almost like 6x. So yeah. So that's where this 128 dimensions really help. That I believe they are focusing more on the handheld devices and like yeah. Um, yes. So these are the like results of this embedding Gemma model. Uh, yeah. So there are like various things that are happening here, but specifically for English, multilingual and code, it performs really better compared to other open weight models. So yeah, like with respect to their size as well. So that also depends. So yeah. So do you want some time to take a look, or do you have any questions? So yeah, so basically these first two, can you see my mouse? So basically these two models are like less than 500 million parameter models, and then comparing against 500 million parameter models, and then closed source models. This is what regularly used by everybody, text embedding 3 large, and comparing against like Gemini. Yeah. So the performance is almost comparable to almost 2x the you know sizes models. So yeah. So yeah, in a whole, like basically like embedding Gemma is a really good model to use on like uh any devices, like not for like enterprise applications, but at least like for personal and other things where you need local models. So
It
yeah,
it seems like Gemini embedding does a better job across the
your
past four
voice is
tasks.
like not clear. Yeah,
Yeah,
Can
your
you hear
voice
me?
is too low.
yeah, too
Is it
low or
better
not.
now?
Yeah, it's getting better. Yeah.
Yeah, so just curious, like Gemini embedding seems to do a better job like across the board for the last four models. Is it like because of the size?
Yeah, so the thing is like size and other things are not revealed because it's a closed source model.
I see.
Gemini models are closed sourced and Gemma models are open, like open weight models.
Okay, I see.
So yeah, yeah. So think of it as like distilled models that they want to have
Right.
on their handhelds like pixels and
Yeah.
stuff. So what they do is they first train the Gemini models, and then
Mhm.
they train the Gemma models. I mean the LLMs, and then
Mhm.
the next step that they do is like they get the Gemini embeddings using Gemini LLM, and take the geometric space and try to embed that within the
Right.
embeddings of Gemma. Yeah,
Right. So essentially like forcing Gemma to essentially replicate what Gemini is doing.
correct, exactly, yes.
Yeah, similar to what DeepSeek
Yeah,
did with like Open.
correct, yes, yeah. So yeah, that's why, like, that's, I believe that's where, like, closed source models like have this advantage to kind of
Mhm.
make the open weights models really good. Yeah.
Yeah, that
So
makes sense.
yeah,
And
but
this
yeah, go ahead.
mean is like this is just like the accuracy on these tasks, and then you just take like a mean.
Correct, correct, exactly, yes.
Okay.
So yeah, so basically there are types and tasks. I didn't look into what task type is, but task is
Mm,
basically at a high level, like, these things.
I see.
And yeah, within type, like based on what I've read, so basically first it looks at the task and then goes into type and then averages within the task, each task. So
Okay,
it does it like that. Yeah.
makes sense.
Yes. So yeah. So like I mentioned, like, so practical applications, low latency, like RAGs, on device privacy, then cost efficiency, then code retrieval. So these work at, like, these are helpful for majority of mobile devices and other things. But yeah.
So have you
So
used
in
Gemma?
yeah.
Have you used Gemma?
Uh, so I haven't used Gemma. Gemma model is not good. Uh, but I believe like embedding Gemma might be better. I haven't used embedding Gemma.
You haven't used embedding Gemma.
Yes, I haven't used embedding Gemma. The thing is, it's harder to evaluate them because you need to have your own data sets. Creating your own data set is a hard part because you need to also have retrieval ranking as well.
Mm-hmm.
It's like, how do you even have, like, when you have 10,000 documents? If it is not 10,000, like, it's not, you know, significant to test this model as well,
Mm-hmm.
right? So yeah, even with, like, closed source embedding models, I had a lot of issues when you have numbers within that, right? I don't know what they call that problem as. So when you have numbers, embedding models cannot understand those numbers properly. Do you guys know the terminology of that? So a lot of medical data, if you want to use embeddings, it's really hard. That's, I believe, that's biggest open problem with numbers. That's
Yeah,
why
I
they
think
use this hybrid approach.
yeah, I think Meher can comment on that. He's been working on something similar.
Oh,
The number.
Yeah, I mean, yeah, numbers embedding is quite like finicky in a way. Also, like the
Yeah.
tokenization and everything for numbers, it is being modeled as they are part of the text. So it's most of the time these embeddings are more frequency dependent than basically showing what the intended meaning of number actually is.
yeah.
So yeah, that's a big problem.
Yeah.
Yeah, actually, yeah. Yeah.
We would like you to present that paper that you were showing on the
Yeah,
lab.
sure. I'll definitely will. So, but yeah, the thing is, I just have to basically understand first of all, like what
Yeah,
is
yeah, yeah.
happening. Once I am done, I'll definitely present that. Yeah.
Okay.
Sure.
So you guys work like on specific topics for a long durations, like I believe PhDs. You guys do that, right?
Mm.
Yeah, I
Yeah.
mean, basically,
Okay.
you have to choose a topic for your thesis, and you
Okay.
work around that. So we can publish papers which are different from the main thesis, but we try to align it with the main study, like whatever we will be defending after all.
Like, okay, it's almost like, it's done, but the thing is, like, I had these questions about PhD because I also once thought, was thinking about doing PhD. But I see this, this defense topics or like titles that these guys have, right? These look very general. Like, some of them write, like, overview of, robotics landscape, and, like, using LLMs, like some very general topic. Like, can defense topics be that general, like, or it
Mm.
has to be that specific? Like who decides these topics?
It
That too
depends
4 years
on
ahead.
like your supervisor as well as how much work you want to put in your PhD. So I
Okay.
mean that's a very subjective question. I would say Daya should be answering that first of all.
Exactly.
Okay. Like
Exactly.
you guys have like 4 years, right? And also, how do you kind of like think, okay, after 4 years this topic is going to be relevant, or you decide the topic 1 year before your presentation, or what?
Daya, please.
Yeah, that's
Okay.
actually
Take the
that's a
charge.
Yeah. Daya can
It's
explain that.
it's a bit of a gamble. That's why you